All right, sweet. Actually, I don't want to disturb them, Dylan. Okay. It's good to be here. I'm glad to be back. I'm sick of my house. It's not my house's fault, you know, just quarantine life. Today we're going to go over 3.11. This is on spectroscopy and the electromagnetic spectrum. How's it going? Good. You're in the same spot. Okay. Where is that? I don't know. One of those spots. That works for me. So the last three topics, we're on the last three topics of Unit 3. Again, this unit was about intermolecular forces, and really the first half of this unit was the big stuff. We're kind of drifting off into a couple other random topics, especially these last three topics are kind of standalone topics. They threw them in this unit for some reason, but they totally could have put them somewhere else in the curriculum. So this is very different than what we've been talking about, which maybe is a good thing. I fell at a decent time because we've had 5 days off, so I have a hunch you don't remember what the heck I was talking about 2 weeks ago anyway. So maybe it's not a bad time for a random topic that kind of can be stuck anywhere. But today, spectroscopy, electromagnetic spectrum, this is kind of physicsy stuff. Really, I mean, especially if you get deeper into physics, a lot of this is very closely tied to physics more than it is to chem. Chemists use the electromagnetic spectrum, whereas like physicists kind of study the electromagnetic spectrum, if that makes sense. So it's a cross-categorical thing we're talking about today. But let's get into it. I don't think this will take me the hour. This better not take me the hour. But that's okay, because you do have homework topic 3, which is going to be due tomorrow night at midnight. It's all old stuff, which is a good thing. I think, again, it's been 5 days off. I have a hunch are not great for anyone, and having me not be here, and I haven't really felt like your teacher for the last 2 weeks, which also makes it tough. So hopefully, by looking at some of the old stuff on topic 3, that'll help too. But anyway, all right. So this is the electromagnetic spectrum. Okay, up top is the entirety of the electromagnetic spectrum. You've probably heard of some of these things, and you might even know some of them. Okay, what is in the middle here, where it kind of gets broken down and spread out, this is the visible region. Now, electromagnetic radiation is the fancy word for light. Okay, we could get into what it actually is. We could get into, again, more of the physics side of things, but we really don't need to. All right. Essentially, if you hear the word electromagnetic radiation, you should think light. Now, for our purposes as human beings, that essentially means the visible region, because we can't see beyond that. Hence, visible, what we can see. But there's a whole bunch of different types of electromagnetic radiation. There are very high energy types of electromagnetic radiation, things like gamma rays and X-rays. You're familiar with X-rays, right? Because you go to the doctor, you break a bone or something like that. You all had X-rays, or the dentist, right? You get dental X-rays. These are very high energy. Okay. When you go to the dentist and you get an X-ray of your teeth, they throw that big lead vest on you to protect you. Overexposure to high energy electromagnetic radiation is not good for the human body. It will cause cancer. It will kill you. Okay. So these, especially gamma rays, zero exposure for the humans, because that's not good for us. We will die. X-rays, very minimal exposure. Okay, it's useful, right? X-rays are very useful for doctors and dentists to obviously observe bones and teeth and things like that. But we want to minimize our exposure. Ultraviolet, you know that one too, right? That's what comes from the sun. That's what you wear sunscreen for, to protect yourself from the ultraviolet rays of the sun. This is another type of electromagnetic radiation. A little bit higher energy than the visible region, okay? And too much exposure, overexposure, and also, over time, eventually cause cancer. What's that? How's it going? Good. Good. Good to see you. Good to see you. Then we get visible. That's what we see. And then we get to the lower energy types of electromagnetic radiation: infrared, microwaves, and radio waves. Okay? So the visible light that we see, the radio waves, which no one listens to radio anymore, but the radio waves, which are also used for your cell phones, I suppose. Of course, none of you talk on your cell phones, so I've got no reference point. I'm just an old man. But this is all part of the same type of energy, the same type of system. Okay? So we're going to use the electromagnetic spectrum in chemistry to do a little math. And chemists, if we had a whole heck of a lot of money, we could do some really cool things with it, because there are instruments in the chemical world that pretty much use all of these different types and give us information or feedback on the chemicals that they're analyzing. So that's where this is heading today. Again, it's kind of a standalone or a separate topic from what we've been talking about. Eventually, we'll do a couple math problems today. They'll be pretty easy, I hope. Or we'll do some math problems tomorrow for sure. One thing I will note here is these numbers, because I do have some numbers here. These are wavelengths in meters. Okay, the visible region runs from 4 times 10 to the negative 7th up to 7 times 10 to the negative 7th. Uh-oh. All right. So this is in meters, right? But we can convert that. More often than not, when we're talking about the electromagnetic spectrum in chemistry, we like to use wavelengths in nanometers. So just for the sake of argument, I'm going to convert this. So if I have 4 times 10 to the negative 7th meters, which is what this is, that's violet or purple light. That's at the very end of our visible region. More often than not, they'll write that as nanometers. Does anyone know how many nanometers are in a meter? Couple more. Couple more. I feel like the next one you were going to say was going to be right. 1 billion, yeah, there's 1 billion nanometers in 1 meter. So that means if you take a meter stick and you chop it up into 1 billion little chunks, that's a nanometer. Let me know if you want to try that sometime. That doesn't sound like much fun. Okay? So that means that a nanometer is 1 times 10 to the 9th. There are 1 times 10 to the 9th nanometers in 1 meter. 1 billion. Okay? So I'm going to convert that. So for every 1 meter, I have 1 times 10 to the 9th nanometers. There we go. So if I converted this out, it ends up being 400. Okay. So 400 nanometers is purple light. Again, when I say nanometers, I'm talking about wavelength. I'll define wavelength next slide. And then the other side, then this would convert into 700. That looks ugly. And that looks ugly. Okay. Take 3. There we go. All right. So again, more often than not, when we talk about the different types of light and we're talking about visible light, we'll use nanometers. The visible region runs from 400 nanometers up to 700 nanometers. That's it. That is the entirety of the visible region. Now, on here, it makes it look way bigger than it is. It's quite literally a sliver. Okay? What we can see is a sliver on this scale. And the rest of it is different types. Yeah. Good there. So electromagnetic radiation are waves of energy generated by electric and magnetic fields, which are synchronized and perpendicular to one another as they propagate through a medium. Excellent. Did that do anything for you? I wouldn't necessarily think that did much for you, but that's what electromagnetic radiation is. It's alternating or perpendicular electric and magnetic fields which propagate into the same direction. That's a physics thing. I don't teach physics. I don't want to teach physics. Again, what we need for this is some math, a little bit of math, and we'll reference some instruments that actually use electromagnetic radiation to help us understand chemicals. So don't worry too much about that. But the electromagnetic spectrum has 7 different regions distinguished by the various properties, and the 3 properties that we are going to look at are these. Okay, wavelength, frequency, and energy. These are the 3 values or factors of electromagnetic radiation that we're concerned with. Okay? Wavelength, that's like how long a wave is. Now, if I draw a wave, I want to switch my color though. I don't like black. That's boring. Are you testing my color knowledge, or do you actually want that? Oh, okay. That means like pinkish, right? Ooh. See, they don't have a connecting area between the pink and the purple. This is an issue. I don't know how purpley I can get it. Can I do like a salmon? I'm limited with my color selections. All right, but a wavelength, if I drew a wave, which this is going to be probably not overly successful. Meh. Not great. All right. But if I were to draw a wave, if I measure from peak to peak, or from trough to trough, if I had kept drawing this out, right, this is one wavelength. And by the way, that symbol, it looks like an upside down Y. That's called lambda. Okay, the Greek letter lambda. So spelled like that, lamb, duh. How am I doing today, Sam? Doing great. Excellent. I feel like a real teacher. Except for not really. The next one is frequency. Okay, frequency is defined as how many waves pass a given point per second. The rate. Okay, so if I chose this as my point in time, and waves are passing by, right, and I timed it out, and I was able to get a rate of how many waves pass that spot per second, that's frequency.
Does it always have to be in seconds?
It can be in different units of time. Generally speaking, it's in seconds. That's the most common. And I don't think AP would give it to you any other way. So it'll usually be per seconds for us. Now this symbol, which looks like a V, is not a V. It's a Greek letter as well. This is nu and U. When I draw it like this, and it doesn't look great. I draw like this side straight and this side kind of curvy to represent the letter nu. It's like a half of a V and a half of a U. That's what my brain thinks, just to kind of give you a sense of what's going on. And then last but not least, the last thing we care about with electromagnetic radiation is energy, capital E. That's an English letter, fifth one in the alphabet. The uppercase version of it, you are unfamiliar. And that is a lame joke. Excellent. How was your 5 days off? Oh, I'm going to fall asleep. I blame my teacher. Okay, all electromagnetic radiation waves travel at the same speed in a vacuum. What is this velocity?
E times c squared.
No.
300 million seconds.
Yes. Where'd you get that from? All right. Nice. Yeah. This is the speed of light. Okay. The speed of light is given the constant c, lowercase c. That's the speed of light. And it equals, according to our AP chemistry formula packet, which, by the way, it looks like this, right? There's a periodic table on the front, and there's 2 pages of formulas. This thing has relevance now, because we're actually did a little math this unit. That was fun. This is in here. On the very first page of formulas, in the top right-hand box, we have speed of light. C equals 2.998 times 10 to the 8th meters per second. Okay, so they use 4 sig. So instead of the 3.00, you might have heard of 3.00 times 10 to the 8th, the speed of light. AP has 4 sig figs, they go 2.998 times 10 to the 8th meters per second. It's very fast. That's pretty darn fast. Okay, about as fast as you can get, as a matter of fact. And we need this for calculations too. All right, there's 3 equations we're going to use. 2 of them are in here, 1 is not, but it's not hard to figure out. And these 2 little equations involve those variables or those units that I've talked about in the last 2 slides. Okay, we have 1 more to discuss, which is lowercase h. Talk about that in the next slide. But you are going to need to be able to identify wavelengths, frequencies, energy. The speed of light is a constant. It's in here. You need that too, though. And then the last thing we're going to need is Planck's constant, or Planck. Planck or Planck. When I was taught, I always heard Planck. But then I watch YouTube videos and people say Planck. Is he British?
No. Well, actually, yes. Now I'm curious. But I think when you watch British, you're like have some kind of foreign accent. I don't think I've ever seen an American do a science video. Not one.
That's right. You know, Shark and I were talking about that too. Like literally, if you're watching YouTube science videos, it's usually British dudes.
Any useful science or math video I've ever watched, it was always British or Indian. Like the guys speaking. Which I love them. They're great. I love it. Never have I seen an American lecture me on any sort of science, except for maybe earth science. But half of it.
I don't remember, but either way, I will tend to say Planck. But if you hear Planck, and if I say Planck or Planck, it's just a dead dude's last name. Okay. I don't know if he's British. I don't know if he did much else. I'm not too familiar with it. But anyway, so these are the equations you need. They're in here. They're right here. There they are. These are the electromagnetic radiation equations. All right. The energy of the electromagnetic radiation equals h times nu. Nu is the frequency. H is Planck's constant, or Planck's constant. The number is 6.626 times 10 to the negative 34th joules times seconds. That is right here. It's in here as well. Okay. Whenever you need a constant for chemistry, like when we were using the ideal gas law a couple weeks ago, the ideal gas law constant R is in here, right there, 0.08206 meters times atmosphere per mole times Kelvin. Okay. If you need the speed of light, it's in here. If you need Planck's constant, it's in here. Okay. You don't have to memorize these things, which is a good thing. The other equation we have is the speed of light equals the frequency times the wavelength, lambda nu. They're very easy. You're given 2, you solve for the other. Or in this case, you're given 1, that's a constant, and you solve for the other. Okay? They're very, very easy math equations to use. But anyway, so this constant is simply the proportionality factor between an electromagnetic wave's frequency and its energy. This is the fudge factor, as I like to call it. Okay, it's how we make the frequency and the energy equal. All right, using various wavelengths of electromagnetic spectrum, scientists can probe atoms and molecules to gain valuable information about the structure and properties of a sample. This process is called spectroscopy. All right, so this brings us to the whole point of this electromagnetic spectrum stuff. Chemists and scientists use the electromagnetic spectrum to analyze chemicals. Okay? Way back in Unit 1, which I have a hunch you don't remember anymore. Way back in Unit 1, we talked about PES, photoelectron spectroscopy. We did. I promise we did, whether you believe me or not at this point in your life. We did. And when we talked about that, that was a type of instrument. That instrument uses gamma rays and X-rays and bombards chemical samples with gamma rays and X-rays. Now, when you hit chemicals with that high of energy, what happens is all of the electrons basically just get ejected. So a PES spectrum, that was the one where we had like peaks, and those peaks represented the different orbitals. Okay? The way that instrument works is by hitting a chemical sample with extremely high energy radiation to remove all of its electrons. And then they capture the electrons to see how much velocity they have. That's one type of spectroscopy. using gamma and X-rays. There's other types. There's ultraviolet spectroscopy. Uses ultraviolet light, and you hit a chemical sample with ultraviolet light. That will give you different information. You can hit a chemical sample with visible light. You can hit a chemical sample with infrared, with microwaves. Okay? All of these different types of electromagnetic radiation have different energies. And when you hit chemical samples with different amounts of energy, they do different things. And if you can analyze what's happening, you can determine what type of chemical you have. So that's what spectroscopy does for chemists. There's a whole bunch of different instruments that use a wide range of different types of electromagnetic radiation, and you just hit chemical samples with it and kind of learn some information about it. Very useful. It helps scientists figure out structure, meaning like the structure of whatever they're looking at. It helps chemists figure out the types of bonds, the types of elements, and again, the arrangement of those elements, all sorts of various important things by using this type of electromagnetic. So anyway, so previously, hey, that's what I just said. We talked about PES, and PES, you hit this with some high energy electromagnetic radiation, X-rays, you remove electrons, and it tells you about the orbitals. Okay, that's a very useful thing to know. So there are many other types of spectroscopy that scientists use. The underlying principle of spectroscopy is the same in all cases. Use some form of electromagnetic radiation to determine some information about a chemical sample. Now, there are two types of spectra. Spectra is the plural of spectrum. When I say spectrum, that means like the graph that the instrument gives you. Okay, so when it was PES, you had like, again, we had a x-axis, y-axis. The x-axis was the binding energy, in other words, how strongly the electrons were held. The y-axis was the abundance of electrons. Not that you remember that probably, but whatever. But the graph that the instrument makes, the graph that the machine gives you, is called a spectrum. Okay? There's two types. You have absorbance or absorption spectra, and what this means, or what the instrument is doing, is it's determining how much the sample is absorbing. They hit it with a wide range of energy, and they see what travels through and doesn't get captured by the chemical. Okay, what was absorbed by the chemical? This is called an absorption spectra or an absorbance spectra. The other type, which is on the next slide, is called emission. They're measuring the opposite thing. Absorbance spectrum measures how much electromagnetic radiation was absorbed by the sample. An emission spectra measures how much was emitted by the sample. Okay, and I'll switch slides in just a second. So depending upon what instrument you're using, what type of electromagnetic radiation you're using, sometimes these instruments are doing absorption spectra, meaning we're measuring, or the scientist is measuring, how much of a certain type of electromagnetic radiation is absorbed by the chemical. Other times, the scientist is measuring how much of a certain type of electromagnetic radiation the chemical sample is giving off, is emitting. Okay? There's absorption spectra and emission spectra. Absorption, how much did the sample absorb? Emission, how much did the sample give off? And what types of radiation? This on this side. Okay. All right. This little chart is very useful. This is one of the few things that you need to know about the electromagnetic spectrum on the test. Okay? The type of information you get from a chemical sample depends upon the energy of the electromagnetic radiation that a scientist uses. We have all different types of electromagnetic radiation. There are very high energy X-rays, gamma rays. There's very low energy radio waves, microwaves. And then there's infrared, visible, and ultraviolet in the middle. When you hit a chemical sample with different types of electromagnetic radiation, different things happen. If you hit a chemical sample with microwaves using a microwave spectrometer, which is an instrument, what you can determine are the different types of molecular rotations. Microwaves can detect rotation of chemical bonds. If you hit the same sample with infrared electromagnetic radiation, you determine molecular vibrations. Single bonds, double bonds, and triple bonds vibrate with different energies. And using infrared, you can determine what type of bond you might have in a chemical sample. If you use visible and ultraviolet, these are when electronic transitions occur. What that's trying to say is that electrons become excited, they jump up to a higher energy level, and then they fall back down. So they're transitioning between different orbitals, transitioning between different energy levels. And then last but not least, if you use really high energy stuff, you're just ripping electrons completely off the sample when you hit it with X-rays and gamma rays. And when you do that, that helps us determine orbitals. That's what PES is, photoelectron spectroscopy. It uses very high energy X-rays. And all the electrons are just removed. But that's useful too, because then we can determine what orbitals they came from. So these are the different types of electromagnetic radiation that get used in science or in chemistry. And this is the information that they tell us. If you use microwaves, you learn about molecular rotations. If you use infrared electromagnetic radiation, you learn about vibrations. If you use the visible ultraviolet, electrons are transitioning between different orbitals. And if you use X-rays, you're completely removing electrons. All useful stuff. Okay? All useful stuff that chemists use and need. So using multiple methods of spectroscopy on an unknown chemical sample, scientists can determine a complete chemical structure and have a very good understanding of the properties that the sample has. Since most of the instruments used in these various types of spectroscopy are rather expensive, you are not required to know or understand any of these specific instruments, which is a good thing. I took a class on instrumentation in college. It was not my favorite. It was a semester course where all we did was learn about a new instrument every 2 weeks or so. Yeah, it was okay. It was okay. But anyway, it's all expensive stuff. We don't have any of it because we're a high school. If you go to a university anywhere, they pretty much have all of it. Okay, maybe not a PES. I think PES is very, very expensive. I don't think Madison probably has one, but I don't know if any other school in the state would. But anyway, these instruments are at universities all over the place. So what AP wants you to know is which type of radiation is used to determine which type of property. That's all they want you to know. Basically, this. So with that in mind, maybe, let's try this one first. A chemist is using microwave spectroscopy on a chemical sample. What information will they receive from a spectrum using this type of electromagnetic radiation? What will they learn? If a chemist hits a chemical sample with microwave radiation, what would they learn about the chemical sample? Sam.
I mean, they would know it as, does it mean that they know, like when it says the properties of chemical sample discovered, and it says like molecular rotations?
Yes.
I'm just wondering, does that mean it only has that property under microwaves? Or is it like, is that just like a general property that it just like has, like a passive thing?
Yes. So a chemical sample would passively have various rotations. By using the microwave spectroscopy, you could like determine what rotations are occurring. That make it worse?
You determine what type, like there's different types of rotations?
Yes. Yes.
What if does every molecule have molecular rotation?
Not every molecule has molecular rotations. Most do. So it's yeah, it's not really an absence or presence of it per se. It's more of like a type of rotation that is there. That makes sense. Long story short, all I want you to take away is that little chart. Okay, we'll do some math tomorrow with those two equations on your formula packet, and that's pretty easy. But in terms of spectroscopy and how this gets used by a chemist, the different types of radiation give different feedback or different types of information from a chemical sample. So number 2, various chemical bonds can be detected in molecules based upon their vibrations. For example, single, double, and triple bonds between carbon atoms all have unique vibrational energies. Which type of spectroscopy would a chemist use in order to determine the types of bonds present in a chemical sample? Sam?
Infrared.
Yeah, we want to use infrared, which I will abbreviate IR. Okay? We want to use IR spectroscopy. My spelling. Back. Tra. I was going to say that's right. Scopy. Okay, infrared spectroscopy. What this does is it gives you vibrational information. Okay, different atoms have different types of chemical bonds between them. They have different vibrations in that chemical bond. And an infrared spectrometer can determine the types of vibrational energies that are there. Single bonds, double bonds, triple bonds, or even single bonds between different elements have different vibrational energies. And an infrared spectrometer can determine what you got. That's important. It's important to know what types of chemical bonds are there. Last but not least, the following absorption spectra is for beta carotene. Beta carotene is a chemical substance, okay, based upon the wavelengths that this spectrum is generated over. What type of chemical information could a scientist determine from the spectrum below? Now, this is a little more convoluted. Okay. I have a spectrum from an instrument. And the question is what can this tell me? Well, depends upon what kind of electromagnetic radiation was used. Okay? Well, it doesn't say. It doesn't tell me what type was used. Can I figure it out? How? Uh-huh. Correct. I have wavelengths down here, right? That's like the length of the waves that are being used. They're in nanometers, and this graph that I got from this instrument is running from 200 to 600 nanometers. Okay? So 400 is where the visible region starts. From 400 upward, that's all visible. Okay? This is all visible light, or visible electromagnetic radiation. But we got a little more. We don't just have visible, we have something else. What is this? What type of electromagnetic radiation is over here? It is. This is ultraviolet. That's a U. UV. Okay. So we are using both ultraviolet and visible light from this spectrum. And the reason why I can determine that, or how I know that, is because of the wavelength that the graph or the spectra was given to me. So this is ultraviolet and visible. There's an instrument called a UV vis spectrometer, meaning it uses ultraviolet and visible light to bombard chemical samples. Now, what the heck does that tell us? What does UV vis, or ultraviolet or visible light, determine or test for?
Electronic transition,
Electronic transitions, what the heck does that mean?
when the electrons get excited, and they switch levels.
Yes, electronic transitions. Okay. This is basically helping us to determine the energy levels of all the electrons in the chemical sample. When you hit a chemical sample with ultraviolet or visible light, sometimes the electrons become excited. They absorb some energy, they jump up to higher energy levels, and then they fall back down. We'll talk more about that tomorrow. But for today, that's all I have. That's all I want you to kind of figure out, okay? There are multiple types of spectroscopy that occurs in chemistry. We've got the big electromagnetic spectrum, okay, electromagnetic radiation spectrum, from gamma rays all the way down to radio waves. You can use electromagnetic radiation to hit chemical samples and learn different information. Basically, the chart is what you need to take away. If someone is using infrared spectroscopy, that person is learning about molecular vibrations. If somebody is using X-rays, they're probably learning about orbitals. That's a PES. It's ripping all the electrons completely away from that chemical sample. The long story short, spectroscopy gives us a whole bunch of different tools, a whole bunch of different ways to analyze a chemical sample and learn different pieces of information. Does it get complicated? Yeah, really, really quickly, okay? And you don't need to know the complicated stuff. You just need to know the general, generic stuff. Pretty easy. Sound good? Sweet. I'd like you to spend the rest of the time then working on your homework topic 3, which is due tomorrow. If you haven't finished 1 or 2, I'd recommend going back there. But if you have finished those, you're kind of good. Or we can hang out and talk too. I don't care. Doesn't bother me.